Welcome to Real Physics. This is about the Machian Gravity Meeting recently held in Bonn with Dennis Braun, Jonathan Fay, Jan Preuss and myself. The talks and discussions are a little bit more technical than usual, thus if you're interested in the details I encourage you to look up my variable speed of light playlist or the papers linked in this video. Enjoy watching. So, welcome to your talk. Jonathan Fay, he doing his PhD on Dennis Sciama's PhD, very interesting, and he is the one responsible that I really discovered the significance of Sciama's paper, and we're really delighted to see your talk now about Mach's principle, Mach's hypothesis, and Reisner's hypothesis.
Yes, my PhD is extended a bit further than just on Dennis Sciama's PhD, and I've ended up doing a lot of different things, and also I should say it's in the philosophy of physics, so it's not a physics PhD. And so what I'm doing is really more like foundational work, for trying to get to the philosophical foundations of physics, more than simply, not so simple, but more than just looking at physical models and so on. And so what I'll talk today about is, I'm not going to look at a particular subject, but sort of give you an overview of the different things I've been arguing for in my thesis over the course of my research in my PhD. And so I'll just give you like a broad overview and hopefully try to present it as in such a way that it kind of, you can sort of see how I'm trying to bring things together into a whole, and we'll see how helpful this is to what you guys are thinking about. Okay, so Mach's principle, Mach's hypothesis, and Reisner's hypothesis. I don't mention Sciama here, but I will mention him a little bit later. Okay. So this was the first paper published. Okay, the content slide hasn't got the rest of the content. It's just got the beginning. So here we go. The beginning of the content. I made these quite quickly. I didn't have much time. Okay, so this is my paper that I published on the title Mach's Principle, Mach's Hypothesis, and basically the argument I wanted to make in this paper is to distinguish Mach's principle as like this formal requirement that you can sort of apply to any theory from his hypothesis about the origin of inertia, which is really, it's a hypothesis that is either true or false, and that's the kind of the claim I want to make there. So Mach's principle is based on this idea that, based on this kind of fundamental epistemic constraint we have, that we can't observe absolute motion, right? And so we should get rid of reference to absolute motion in our physics. And on the other hand, and this should be asserted, sort of whatever theory you have, like whatever the empirical content of your theory is, you should be able to say that this should be the case. But then what I'm calling Mach's hypothesis is the specific claim about the origin of inertia, that this very intuitive idea that inertia might have its origin in the masses of the universe. And I also went into some of Mach's reasoning and some things that have been missed in the literature on Mach's principle, in the philosophy literature, where what I think he's really doing is revising the classical concept of causation. So he insists that we make this mistake when we think of cause and effect to isolate a single cause, right? So he gives an example of like Archimedes' proof of that the scale falls on one side, or it doesn't fall on either side because it's balanced. And Archimedes says that the scale does not fall because of a lack of a sufficient reason for it to fall on one side or the other. And Mach says, no, this isn't the case. Actually, it's not the absence of a cause, but it was caused by the fact that the scale is balanced. So that's Mach's claim there. I think you have exactly the same thing with regards to inertia, that in Newtonian mechanics, inertia is motion in the absence of causes, right? And Mach's point is to say, well, how do you know that it's in the absence of causes? There's always this background universe, and so maybe homogeneity of inertial motion is an expression of this homogeneous influence of the environment of the entire universe. So I try to articulate that way of thinking about Mach's hypothesis and his principle, right? Okay, and then Shamas Model, so I got the screenshot from Alexander's video, which was so in this paper I wrote, I claimed that based on Shamas' Machian model of inertia, you could derive the force of gravity. So basically, in very broad terms, if you accept Mach's hypothesis that inertia is not uncaused motion, but motion caused by a homogeneous background environment of masses, well then, it turns out that the background of masses, this physical cause of inertia, is not actually homogeneous, right? They're not homogeneously distributed, and therefore we should expect that inertia is not this purely homogeneous, that inertial motion is not this rectilinear uniform motion, right? And we should expect some deviation from that, and the claim is that you can get gravity out of that gravity just is the inhomogeneity of the relative inertial law. And an important thing to point out is that Sciama didn't make this claim himself, and I think there's some sociological reasons why that didn't happen, because of how like physicists, the way physicists thought by the 1950s had changed from how they were thinking further back, where and as we'll see, Reissner made a claim closer to what I'm saying. So the model works with this neat analogy with electromagnetism. I'm not going to go into the details here. And then, so another thing I've been working on very recently is then I looked into the possibility of some kind of historical precursors to this idea that gravity could be shown to arise necessarily, right? And the only one I found is in this paper by Hans Reissner, or like the main resource I found is in this paper by Hans Reissner. Hans Reissner, this isn't, the first picture isn't Hans Reissner. It's actually, that's Emanuel Friedlander. He's the first person I found who suggests unifying inertia and gravity along these lines. And he was doing something very close to Mach in 1896. And he and his brother wrote this book called Absolute oder Relative Bewegung. You guys will understand better than me. And he, in his footnote, suggests that the true relative law of inertia will only have been found once we unify gravity and inertia in some kind of analogy with electromagnetism, right? And he already had this intuition in 1896, which is remarkable. But Reissner, I think, was the first person to articulate the hypothesis explicitly. And this is like a quote from his paper of 1915. Okay, yeah, shouldn't have a dash. If I'm successful, gravity would be understood as a direct and necessary consequence of the relativity of acceleration. The identity of the gravitational and inertial masses would be shown to be self-evident, and the gravitational field would not only be equivalent to an accelerated space, as Einstein proposed, but gravity would itself be identified as a resistance to relative acceleration. So that's my translation from Reissner's paper, which is in German. But that claim, I think, is like, and this appears in 1915, published in 1915. He writes this in 1914, so it really goes back, over 100 years. This idea, but it was never really picked up. Reissner's paper sort of faded into obscurity after this, and Schrödinger's paper is actually very similar to some of Reissner's papers. This pair of papers he does. Reissner was an aeronautical engineer. He's actually the first person to build an all-metal aircraft. So he was quite an accomplished guy. He also derived the Reissner-Nordstrom metric in 1916. So just after this work, he was following Einstein's work, of course. So he ends up going back to engineering after this, and so doesn't pursue this kind of theoretical physics stuff that much more. So I've been calling this this idea, this hypothesis, the Reisner-Sciama hypothesis, and I'm trying to publish a paper on that. Then one of the other things I've been doing is trying to provide like a provisional philosophical framework in order to interpret these ideas and sort of persuade people to have the kinds of intuitions that I think we share here about Mach's principle, about the gravitational constant needing an explanation, and so on. So this is, I'm really sort of going out on a limb here, and I'm attempting to sort of make contact with the Kantian tradition in philosophy, because at least my personal reading of Kant kind of like resonates with a lot of these ideas. The idea is that by constructing a philosophical framework, then we can articulate and interpret this hypothesis properly, that the gravity is seen as necessary, and that we can actually explain why gravity exists and so on. And if we don't do that, we'll keep coming against these other kind of philosophies of science that don't see this as even valuable, right? And they will keep pushing these kind of speculations to the side because they have different aims. They see science as having different aims. And essentially, so to sort of summarize my framework very briefly, the key result is that there's two issues in classical mechanics that have to do with the fact that a law that's meant to be universal has arbitrary and therefore unjustifiable elements. And the idea here is that if a law is not universal, say a law applies to just this table, so I have like some description of how things happen on this table, then the law having some arbitrary elements could be explained insofar as this table has an environment that I could refer the particular content of that law, I could refer to that environment. I could explain in terms of it being particular to this situation. But if it's universal, so if I try to describe things in terms of universal laws, then there's no external environment to refer to. And so what is it that can justify that a universal law is one way rather than another, right? There's a kind of philosophical problem. And this appears twice in classical mechanics, I claim. So the first case is that the universal law of inertia in classical mechanics is only valid for this preferred set of reference frames, right? And this is Mach's principle, basically, this problem. And the reference frames we know a posteriori, but we can't justify them a posteriori because the law is meant to be universal, right? And so we can't justify it as like this contingent matter of fact. We can if we're looking at subsystems, but not with the universe as a whole, right? And secondly, so we want a law of inertia that's either generalized to all frames or have like a law of inertia that's dynamical and explained as a material interaction. And the second issue is that the universal law of gravitation in classical mechanics has this particular coupling strength. Well, it exists in the first place, so why does it exist? And why with this particular strength, which we can only measure this strength a posteriori, as in we have to do experiments to measure the strength, but it's meant to be universal, and so what is it that's going to justify it? If it's universal, but we only know it a posteriori, right? So we can't justify it. So I'm claiming that both of these problems, the problem with the gravitational constant and the Mach's principle, really have the same kind of like intuition behind them, right? There's the same kind of problem. Involve an analogous type of reasoning. So universal laws cannot be contingent on anything. They must be justified as close as possible on a priori grounds, right? And so I'm attempting to sort of lay out this kind of position in philosophy of science. Okay. So is this a new kind of rationalism? Are we trying to derive the laws of nature a priori without appealing to experiment and then explain? So I would say not exactly. So my aim is really to do what Kant I think was trying to do hundreds of years ago, to properly distinguish which part of science is empirical, the property that comes from the senses, and which part is part of our method of how we're arranging empirical facts according to to principles of reasoning and mathematics, right? Because in science we have to apply mathematics to the world. The world never fully perfectly conforms to mathematics, so there's always some kind of idealization involved in modeling physics. So I also get into these issues in a lot more depth in my thesis. So I'm not claiming we can deduce all laws a priori from the armchair, right? But we should try to construct a framework in which we are explaining natural phenomena, not merely describing them. That's what I'm claiming we're trying to do, right? We don't want this purely descriptive account of reality in science. We want to get to the bottom of like why is it this way, right, and not some other way. Okay, and then I have this whole thing on flat space in my thesis as well. That I just had this paper accepted for publication as well. So what I pointed out in this, and it's connected to this whole kind of like philosophical framework I'm trying to construct, is there's this tension between, and there has been for over 100 years, or hundreds of years even, I go all the way back to Newton, there's been this tension between methodological and physical roles of space. And not just of space, but of many different things in physics. So symmetries and relativity principles, are they, I'll start here. Symmetries, so are the symmetries of space part of like the method of physics, or are they some empirical discovery, right? Is the relativity principle like an empirical discovery? Could it have not been the case? Or is it part of like the method of physics? Like this question really bugs me. Also, energy conservation. Is it the case that energy conservation was discovered empirically, or is energy conservation just part of how we reason about things? So if I was to find, for example, that energy is not conserved in a particular system, I have two choices, right? I can either say it's a miracle, energy came out of nothing, or I can say there must, in principle, supposing causality, there must have been some antecedent form of energy that I haven't measured yet, that I don't know what it is yet, and I'm going to, that got converted into the energy I can measure, and then I can use that to look for what that energy might have been, right? And so it's part of how we reason rather than just being this empirical discovery. Also, the law of inertia, there's this kind of tension between the law of inertia as an empirical result, that things seem to go in straight lines with respect to one another in the absence of gravity. But at the same time, the law of inertia is part of the definition of force in Newton's system. So I think all of these, also geometry, geometry that we measure, like in general relativity, is fitted to like rods and clocks, versus geometry as like a coordination system, like a way of like coordinating different things that happen in different places and putting them in the same description. And what I claimed is that all of these have this kind of dual status, that you have on one hand this methodological concept, and on the other hand this like physical role, this physical status or physical role that it has in science. And I think Mach's principle is best formulated once we have acknowledged this methodological concept of space in science, and that's what I think Mach does with Newton, is he sees space as this purely like mental, like methodological thing that we introduce, and so it can't have like a physical role, it can't be responsible for the inertial forces, and therefore he looks for a different material cause for inertia. Okay. And when I was making arguments along these lines with geometry, I rediscovered this older idea, it goes back hundreds of years, that the mutual independence of shape and size can replace the parallel postulate in Euclidean geometry. And basically, to put it very briefly, you can derive based on kind of relativity requirements, considered in this kind of methodological sense, you can derive Euclidean geometry, you can derive the parallel postulate. And this was discovered all the way back in 1663 by the first guy, John Wallis, and then it was also kind of like revived by Joseph Delboeuf, who was in Bonn, in fact, when he wrote a book on this. So he was a Belgian philosopher and mathematician. So yeah. So in summary, what am I trying to do? Yeah, so I'm trying to explore all of these intriguing hypotheses and uncover their history, find like who are the people in the past who have like thought along these lines, and kind of like map out like how all of that developed, and then construct like a new conceptual framework, and thinking about like what are relativity principles, what is energy conservation, are there like special constraints that we can place on cosmology that we can't place on subsystems of the cosmos, and that's involved with the Mach's principle. And what is the role of mathematics in science? What part of science is a priori? What part is like coming from the senses? What is empirical, and so on? And then my hope is that by laying this conceptual groundwork, we can this will allow us to understand these kinds of hypotheses and develop them further. So yeah, that's my ultimate aim. Okay, there we go. I hope that was not too long. Was it?
No, that was perfect. 13 minutes. Thank you very much for giving this historical perspective. It's a way of doing science I really like, and it's your merit that you have discovered many people I wasn't aware of. One of them, Reisner, and it's really exciting, and I guess we can learn a lot of if you don't miss this look at history. I also like the remarks I've made about epistemology, and well, I have two remarks on that, but maybe one has two more spontaneous reaction.
There was one question I would like to ask. You were when you were talking about Mach's principle, you said, okay, this uniform motion without any forces in Newtonian mechanics is related to the homogeneity of the universe somehow. And I just wanted to ask, was this the way that Mach originally formulated it, or is this your interpretation?
No, so that's partly, I mean, the trouble is with Mach, and I go into this depth in my paper on Mach's principle, Mach's hypotheses, is that he, the way he articulated his principle, especially in the Science of Mechanics, is he avoided referring to causation at all. Like he had this very like positivist style of writing, and so he would just refer to experiences and correlations between experiences. And so he avoided referring to causation because causation was this metaphysical concept and so on. And so, but in his early writing, he did refer to causation more explicitly. And so what I did was, by comparing some other things he'd said in both his early writing about Archimedes' proof that I mentioned as well, that he mentioned it both in his book on the conservation of energy and then in his later The Science of Mechanics. And he basically says the same thing, but he changes the language and no longer refers to causation in the second one. But he makes the same critique of the causal law, right? That we've neglected environmental circumstances. And the point I wanted to make is if you follow that kind of reasoning, you can reconstruct Mach's principle in that way. I also draw from the particular quotes and show how they're very similar to what I'm saying. But that particular way that I explained it is my own like reconstruction, or like based on his reasoning applied to other things, then applied to inertia gives you exactly this. But yeah, I hope that clears it a little bit. But
to some extent, yeah. No, I was wondering if already Mach was aware of this conceptual idea that you could unify inertia and gravity through his idea, or if this
of course.
was...
I guess he stated this explicitly.
So I think
so he preceded Reisner, actually.
Well, I'm not so sure about that, because I think he does. I think he actually gets it from the Friedlander brothers, because I think in his earliest writing he doesn't really mention any connection with gravity, but then in like later editions of the Mechanic, which are published after the Friedlander write their booklet, he mentions the Friedlander brothers, and I think he does. But again, the language is, and those editions are only in German as well, so I haven't been able to look at the whole book like very closely. But I found some passages, and I think he's less explicit than we would expect, based on like how most physicists have cited him about like a connection with gravity. I don't think he's necessarily the originator. But the Friedlander was the first one, I think, and Einstein really goes for this connection with gravity with his equivalence principle. And Reisner is following Einstein, so Reisner really, like, was doing something very similar to Einstein, but I think a bit more coherently in terms of like the application of Mach's principle.
Yeah, but it's quite obvious that you have this inertial aspect of masses and the gravitating aspect, and I guess all this talking about Mach's principle. The masses in the universe being the origin of gravity. It's not just.
It is like
it's not completely unfounded, no, right? So, you might be right that it's hard to make this explicit, but somehow it's clear that going further from his thought experiment about Newton's bucket, right?
But the peculiar thing about Mach is, again, like I think his positivist style gets in the way a little bit because he doesn't have this like view.
His own reasoning.
Right. He doesn't have this view where there would be amenable to this notion of like unification as being like this great. Like he stays more. He's just saying like, and the way he writes it, especially in the Science of Mechanics, a very like humble empiricist view that he just says, well, we don't really know that that inertia is. How does he say it? He says we don't really know that inertia is defined with respect to an absolute space because we can't observe absolute space. We only know its correlation to other bodies, in particular the distant stars, which seem to stay in constant relation to the inertial motion. And then what he says is he gives two suggestions. Either the distant stars have a collateral role, is it something like zufälliger, and something else like in German, or a fundamental role. Maybe that's the. So either there's a collateral role that the distant stars are playing, as in there's like an absolute space or something like that, and the distant stars are stationary in that frame, and then the inertial motion is also stationary but they have a common cause, right? Or there's a fundamental role that they play, i.e. they causally influence the inertial motion. But Mach doesn't like to use the word causation, so he just uses like collateral and fundamental role of these experiences, right?
The audience is continuing. I'm just changing to that.
Yeah, no problem.
Dennis, do you have any? I have still one comment, but maybe Dennis, you have.
Yes, I was just at the end. You said something about the role of mathematics, and I think this is also a really interesting question.
Right.
About which role does mathematics really play, and I think many physicists today think that mathematical principles are some kind of guiding principles in physics, but this does not have to be true, because physical principles as the guiding principles of physics, and mathematics was more just the language in which they are expressed.
Right.
And I think to clarify this question, which one of those two is really true, is also yes, I think it is an important question which needs to be answered.
Yeah, and also to properly distinguish between physical principles and mathematical principles, which
of course
I think physicists will often not like be attuned to these distinctions. Yes, it can cause some confusion. So there's this long controversy in the history of geometry, especially in the 19th century, because of it seems to, on one hand, be like this mathematical a priori, like Euclidean geometry. You can deduce all of the propositions a priori, and on the other hand, it's applicable to reality in this really, like, a very precise way, right? And so, where does it come from? And people have different ideas. You know, is it like it can, like, reasoning give us knowledge about the empirical world or something like this? Or is there some kind of like pre-established harmony between the mind and the external world? There was all sorts of kind of speculations like this in like early modern philosophy. And in the 19th century, people had like a more empiricist critique, and they start questioning whether Euclidean geometry is even precisely correct, right? And this was, I think, the crucial time when we could have got out of some confusion, but we ended up going into a different confusion. And this will connect maybe to what you were saying also about Minkowski, blaming a lot on Minkowski.
Maybe too much.
But I think it goes even further back to before that, because just around this period, there was the possibility of like properly distinguishing between like geometry as this like methodological thing, as it and all of these principles as kind of like methodological things, and on the other hand, like a separate thing of geometry as like this physical field, like the metric that you have that determines how things move and so on. And those are two different concepts altogether, right? And I think they were not properly distinguished, and Helmholtz and Poincaré have these really great investigations. They're attuned to the subtleties, but I think they end up leaving some arguments aside, in particular these arguments about the relativity of scale that I talk about in this paper. And if we could go back to that and like revisit the concept of space and move away from placing, I mean the whole framework nowadays is like placing, you have like a topology or something like this that doesn't even have geometry, and then you have all of these possible geometries that it could have on equal footing. I think there's some conceptual problems with how all of that has been set up in physics and mathematics. So I think that this late 19th century is a really key period to look at if you want to like get out of some of the conceptual problems that have like influenced how physics has developed like since then, I think.
Yeah, I have two comments still. I guess methods have taken over in modern physics too much, and we already discussed that people are believing in methods, in formalisms, instead of how nature works, and just focusing on the observations. And I wouldn't be too reluctant if there was a possibility to derive the laws of nature from the armature, as you said. I kind of even like the idea. I mean, of course, you shouldn't lose touch with reality as other physicists today must do. But as a matter of principle, that's a nice idea. On the other hand, I would claim that there should be no gods, no numbers accepted.
Yeah. No excuses.
Yeah, no excuses, and no artificial, no numbers which, in Einstein's words, the mood of the creator could have been chosen just another way.
Exactly. Yeah. And I really try to like lay out what is the fundamental intuition behind this kind of reasoning that I think we share. Yeah.
More specifically, one point you mentioned energy, and where does the concept from? Actually, I would claim that energy is a complete invention of physicists who just had the desire of making the laws of nature time independent.
Right.
Yeah, that's the possibility.
Exactly. I think you're absolutely right.
I don't want another law of nature every 5 minutes, and that energy is the very nice and very intelligent concept that allows you to deduce that from a simple principle, for which, however, there is no observational evidence if you consider cosmological scales. I mean, we might very well miss a slight change in energy, this and there, in the following the cosmological evolution, and that's why we have to be very attentive to observations in this domain. But there's no necessity to stick to the concept and hell is something God-given. No,
Well,
no.
Well, yes, but I think it's still fundamental in the sense that we
Of
necessarily
course, I mean,
do want to describe things in this time-independent way. But I agree, that's exactly where it comes
yeah.
from.
I mean, if you replace it, I mean, we need to generalize it in even a more smarter way. Yeah, but
Right.
not necessarily. It's something we wanted actively to keep the laws of nature time independent. Of course, momentum is independent of
Space,
independent of space and angular rotation independence and so on. So that's the simple thing behind it.
And of course, you know, like somebody might say, well, what if the laws of nature are not time-independent? But the answer to that is really, well, if the laws are changing, and they're changing according to some actual pattern, then there will be laws by which they change. And then if you describe the things in terms of those meta-laws, then you will recover the time independence, right?
Yes.
And so it's a kind of like tautological thing and Mach, interestingly, has, I think everybody should read this book. He has a really nice little book called Conservation of Energy, or like History and Root of the Principle of Conservation of Energy, which is his first book, where he also has, I think, the cleanest articulation of his principle in the notes at the end. The one actually that Shama cites is from this book.
Mm-hmm.
And in this book, basically what he does is he traces all of the, I mean, there was this kind of like energy mysticism around the time, in the late 19th century as well, where people were sort of thinking, oh, is energy this like magical substance that never dies, and so on, and physics has discovered this magical substance. And Mach wants to kind of like disillusion us and say, really what it comes from, historically, is all these derivations from the requirements for the exclusion of perpetual motion. And the requirement for the exclusion of perpetual motion is really just asserting the law of causality, right? That if you have causation, you don't get like perpetual motion machines that can keep producing motion out of nothing, right? And so he traces all of this back to causality, and then of course, really what you need is causality and time independence of your laws, and then you have energy conservation. Yeah. Anyway, any more comments or questions? I can also, like, if you have any, because I didn't go into any detail about like what I did my thesis.
Yeah.
But if you have any questions.
I guess we continue off camera and then see. Thanks again.